Welcome to Mr. Frolic's physics classes. In this lecture, we will start discussing circular motion. Hello there. In this lecture, we will have as a main goal to talk about forces in circular motion. But before we do that, I need to define and build up a vector description of kinematics, or a analysis of motion in 2 dimensions and 3 dimensions. And that's exactly what we'll start doing now. I am representing here in 2 dimensions only, x and y, although all of what I'm going to say for 2 dimensions will be valid for 3 dimensions. It's just that I cannot draw those pictures. A point or an object at a position P. The vector position of that object with respect to the origin of my reference frame is going to be a vector starting at the origin and ending at P. I'm going to call that vector R. In terms of unit vector and components, we have the following. We have the projection of R on the x direction, Rx, and the projection of R on the y direction, Ry. And we can actually write this in the following way. R equals an Rx plus an Ry. Or, in unit vector notation, which is the more appropriate way, R is going to be an Rx I hat plus Ry j hat. Okay? So this is establishing the concept of position. I should have written this here first, my bad. But it's establishing a concept of position vector. Now, after we have this idea of position vector, let's talk about displacement, because objects don't stay in place, they move around. So now let's talk about displacement. In my description now, my object was at the initial position, Ri, and it will move to a final position, Rf. And as it does that, it follows a path that in a more generic way, it could be seen as somehow, for example, a curve like this. Well, the vector displacement, delta R, is going to be, by definition, Rf minus Ri. In terms of a geometrical representation, I could say that delta R is this here. Here is my vector delta R. And that the vector delta R is going to be on a second line to the overall path of the object. Intercepts the path at the initial and final points. In terms of components, so we have that delta R is going to be a R final x I hat plus R final y j hat minus R initial x I hat plus R initial y j hat. So this is my delta R in unit form, and then I can rewrite this in this way. Delta R equals to Rfx minus R initial x I hat plus RFY, sorry, yes, RFY minus R initial Y J hat, and I hope that that can be seen in the end. Or that delta R is going to be a delta Rx I hat plus a delta Ry J hat. And then this is the vector displacement in component form. Okay, after cleaning up the board and moving the picture up here, now I have my daughter here who believes she's helping me in recording the video, although I don't think that's much help. Going back to our lecture then, after talking about displacement, we need to talk about the idea of average velocity. And average velocity is, by definition, okay.
I'm famous.
Yes, you are. You're famous. Go famously elsewhere. So, after inviting my daughter to leave the scene, let's now just define the next step here, which is the idea of average velocity. And average velocity, V bar, is by definition change in position over change in time. Notice that since the time interval is always going to be positive, I have that the average velocity is a vector divided by a positive number. And this will actually give me that my average velocity is always going to be parallel to the displacement. Now, since the displacement is a second line to the path, the average velocity is also going to be a second line to the path, like this. Next step for us, after defining average velocity, would be to define instantaneous velocity. And the instantaneous velocity, V, is defined the way we always did before, as the limit when time approaches 0 of the ratio delta R over delta T. So the instantaneous velocity then is just going to be, this is the derivative of position, dr, with respect to time, dt. In component form, we could say that the average instantaneous velocity is going to be a dx dt I hat plus a dy dt j hat. But the part that I really want to highlight, that is more important for us, is this here. As my time interval is getting smaller and smaller, the path and the vector displacement delta r get closer and closer together, which means that my average velocity is also getting closer and closer to the actual path. Now, when I take the limit, the time approaches 0, what we'll have is that our initial and our final would be really close together, and if this is the total path the object is moving, the infinitesimal displacement dr on that interval will actually confuse itself with the path, and my instantaneous velocity will be actually a vector tangent to the path and in the direction of motion. So let's keep this in mind, that instantaneous velocity tangent to path. Always. After defining average velocity and instantaneous velocity, my next step is now to define average acceleration, and later on we'll define instantaneous acceleration. So average acceleration is going to be, I'm going to actually write this way here, average acceleration is, again, by definition, the same way that we did before, is change in velocity over change in time. I'm going to hold this definition here for now and move forward quickly. The instantaneous acceleration is going to be defined the same way that we did before. So the instantaneous acceleration is the limit when time approaches 0 of delta v over delta t. And this, of course, is the time derivative of velocity. So the instantaneous acceleration is dv dt, which is going to be a dvx dt I hat plus a dvy dt j hat. This actually is then an ax I hat plus an ay j hat. And when we talk about a normal object moving on a floor, like a robot, moving back and forth on the floor, we could actually use this kind of description, the Cartesian coordinates, more often than anything else. But for the kind of system that we will be discussing in this topic, which is systems that are moving in curved path, in circular path, or an arc over circumference path, this description is not going to be that useful. I will come back and revisit this one here. Focusing again on the average acceleration, since time is always a positive number, what we have is that the average acceleration is always going to be parallel to the change in velocity. And let's use this property to understand a little bit better what's happening, or what will happen. So I have here now an object moving in a curved path. That's the path of the object. And this is an initial time 1 and a final time 2. The velocity of the object at time 1 is here, v1. And the velocity of the same object at time 2 is in here, v2. Well, the change in velocity, delta v, is equal to v2 plus the opposite of v1. So I have v2 slightly down, and v1 was slightly up. The opposite of v1 is going to be somehow this way. And then the change in velocity, delta v, points down this way in my picture. But instead of down, a better reference frame would be this. A curved path, a circumference, would always define an inside or an inner side and a outer side. And what we have is that the change in velocity points inwards, basically, which also tells me then that the average acceleration points inwards in a curve. Now, this is important because if you remember Newton's second law, there is a net force that's going to be parallel to that acceleration. And if my acceleration needs to point somehow inwards, then my net force would also need to point somehow inwards. Let's do a comparison between what we used to see before, the straight line path, with what we're studying now, the curved path. So, I'm representing here an object moving on a straight line path and on a curved path. This object would have a velocity v, and that velocity v needs to be tangent to the path. So here's the velocity v on the first situation and velocity v on a second situation. Now I want to draw the acceleration, and I'm going to assume, just to make the picture look easier to understand, that both objects are slowing down, so that the acceleration needs to be in the opposite direction of the velocity. In this system now, I'm representing the acceleration of the straight line path straight against the velocity. But on the curved path, we just saw that that acceleration needs to somehow point inwards with respect to my path. And because it's slowing down, it also needs to be a little bit backwards. And this is the new representation for us. This acceleration that is a little bit in, a little bit back, can be decomposed into a component perpendicular to the velocity, pointing inwards, and because it is perpendicular, at this point I'm going to call this normal acceleration, and a component that points backwards, is in the same direction of the velocity, but on this example, against the velocity, and that I'm going to call then tangential acceleration. Okay? And this tangential acceleration is exactly the same as what we had before. It's the same acceleration that we had in our previous example. The normal acceleration is actually the new thing that we have in this system. And if we think about geometry, okay, let me just help us out here quickly. This is a circular path. Here is the center of my path. In order to find the normal to a point, the first thing I need to do is draw the tangent line. And so here is the tangent line, which by definition is perpendicular to the radius of the curve in that point. And then the normal direction is perpendicular to the tangent. But you can see from the construction that this normal component is actually always pointing towards the center, because it's going to be radial inwards. And because of this, the normal acceleration is also called centripetal, as in center-seeking acceleration. And that's the word, that's the name I'm going to use more often, centripetal acceleration. When we think about the role of those accelerations, we see that the tangential acceleration was already in the straight line path motion, and it is related to the changes in the speed. So tangential acceleration, it is related or measures changes in speed of the object. And the centripetal acceleration is the new thing, is the one that when I have a centripetal acceleration, I'm going to have a curved path. So the centripetal acceleration, AC, will measure changes in direction of your object. If you think about it a little bit, in a car, if you're driving a car, you will produce changes in the speed of the car by either hitting the gas pedal or the brakes. So you hit the gas pedal, you hit the brakes, you're going to be changing the speed. So you're producing a tangential acceleration. And to change the direction of motion of your car, you need to turn the steering wheel. So the steering wheel will actually then cause for me to change the direction of the object. The centripetal acceleration is what we want to focus now. And in order to study the centripetal acceleration, I will analyze a motion where I only have centripetal acceleration. I don't have any kind of tangential acceleration. Can you guess what kind of motion it is? The motion that we will now use to study is uniform circular motion. Let's remember that in physics, uniform will mean constant. And in terms of motion, when I say uniform, I mean constant speed, please. Not total velocity, but constant speed. And the reason why I'm studying uniform circular motion is this here. If my particle is at a certain position, P, moving, for example, with a velocity V, on a path of radius R, the only acceleration I will have is the centripetal acceleration. If we had tangential acceleration, the speed would be changing, and therefore I would not be doing uniform circular motion. I will be doing accelerated circular motion. So by studying this motion here, anything that I get as a result of my acceleration will now be actually is going to be the centripetal acceleration. And so that's why we're going to study this. Before digging into details of velocity and acceleration, I want to define with you a new quantity that is quite useful when we discuss objects moving in circular motion, which is an angular description. So if my particle is initially at this position here, R initial, and then comes to this position, R final, we have that the vector position will swipe a certain angular sector. And while that is happening, the object is traveling here a certain distance. I want to call that S. Well, the angle that my vector position swipes, I'm going to call theta. The average angular speed we represent by omega, and because average, when I use a bar, is by definition the angular displacement theta divided by the time it takes to go from one place to the other, t. So it's theta over t. In terms of units, any unit of angle divided by time would work for angular speed. But the international unit is radian per second. The faster you get used to it, the better. Now, we have, at this point, a linear description, the arc of the path, S, and angular description, theta. We have a linear velocity, V, and also an angular velocity omega, describing the same motion. And we need to know how to relate these two. So I'm going to start by a cheat from our math classes that tells us that S equals R theta. And if I want to go from here to the speed, I would just take the time derivative on both sides. So ds dt is going to be then d dt of r theta. But if I'm moving in a circle, r is constant. And then the right-hand side, or the second side of this equation, becomes then this here. ds dt equals to r d theta dt. But d theta dt, if we come back to the idea of average angular velocity being theta over t, d theta dt is the instantaneous angular velocity. So the first side of this equation, ds dt, becomes the speed, the linear speed v, equals to r, and then d theta dt is omega. So this equation here will be helpful in the close future. Okay? To finalize this portion of our lecture, let's make some analysis of the position and from there try to reach a conclusion about the centrifugal acceleration. So my object is moving on a circle of radius r in uniform circular motion. Therefore, the acceleration is completely centrifugal acceleration, pointing here towards the center. When the object is at a certain position, its vector position is r, and the angular position is theta. The velocity is tangential and pointing in the direction of motion. So here is my velocity v. Let's remember that the angular position theta is in itself a function of time. And I can start that analysis from here. From omega equals theta over time, theta is going to be omega t, where I'm using the trigonometric orientation and I'm assuming in here that theta naught was 0. Okay. The vector position r can be broken down into components rx and ry. So rx I hat plus ry j hat. Okay? That's basically what I have. Now notice that rx, this component here, is the projection of the position on the x direction, is the adjacent side to the angle theta. But the position here is actually the distance radius from the center. So I can write this r as being r cosine of theta I hat plus the y component would follow the same idea, but now is a projection on the sine axis, or the opposite side to the angle theta. So this would be r sine of theta j hat. Now let's remember that theta itself is actually a function of time. So we're going to have that r can finally be written as r cosine omega t I hat plus r sine omega t j hat. Okay? Well, the velocity of this particle, is the time derivative of position. Now, when I take the derivative of r cosine omega t I hat, r, the radius of my path, is a constant. and therefore it just moves out of my derivative. And so I'm going to get r times the derivative d dt of the cosine of omega t. And I hat is also constant. I can keep it there. Plus, same idea for the y component. R d dt of the sine omega t in the j hat direction. Let's keep on writing this. This would be then r. The derivative of the cosine is negative sine of omega t. Now I need to use chain rule and take the derivative of the argument of the cosine. And the derivative of omega t with respect to t is just omega. Okay? This here in the I hat direction plus r. The time derivative of sine of omega t is just going to be cosine of omega t multiplied by omega from the chain rule in the j hat direction. So this is my velocity. I'm just going to now reorganize this and write it in a different way. Kind of like this here. My velocity then is going to be negative r omega sine omega t I hat plus r omega cosine omega t j hat. And I would ask us to hold this. I'm going to clean up the board and then finish the calculations. So I'm now going to just organize the two results we have and make room for the next step. So our position vector is given by r cosine omega t I hat plus r sine omega t j hat. The velocity is given by negative omega r cosine omega t, sine, my bad, sine omega t I hat plus omega r cosine omega t j hat. Now I want to know the acceleration. And acceleration, the acceleration is, of course, the time derivative of velocity, dv dt. So I need to take the derivative of these terms here. But again, r omega are constants, and they are not affected by the derivative. So what I'm going to have is basically negative r omega. Now the derivative of sine of omega t is going to be cosine of omega t multiplied by omega in the I hat direction plus here again r omega is not affected, r omega. Now the derivative of the cosine of omega t is going to be negative sine omega t. This also needs to be multiplied by omega because of the chain rule. Finally, j hat. Notice that I have here two things I can factor out. Or let me rewrite this way finally. Acceleration then is going to be negative r omega squared cosine omega t I hat minus r omega squared sine omega t j hat. And this I can factor out. I could actually factor out negative r omega squared but I don't want to do that. I want to factor out the negative and the omega squared. And then acceleration will be equal to. So the acceleration now is equal to negative omega squared, I factor out from the two terms I had in here, that multiplies r cosine omega t I hat plus r sine omega t j hat. Now, we can identify that r cosine omega t I hat plus r sine omega t j hat is actually my vector position r. And then this equation now can be written as the centripetal acceleration equals negative omega squared r. In terms of direction, this tells me that that acceleration is centripetal because the vector position r is radial outside, and my acceleration being negative, that needs to be radial inside, which means centripetal. And in terms of magnitude, I have that the acceleration centripetal is omega squared r. So this is the centripetal acceleration expressed as a function of omega, the angular velocity. If you remember that we saw a couple minutes ago that v equals r omega, I can solve this equation here for omega. So omega equals v over r, and then I can plug omega back into my centripetal acceleration equation. So centripetal acceleration is going to be then v squared over r squared multiplied by r. This first term here is omega squared. So the centripetal acceleration at the end is going to be v squared over r. And this is the second equation I have to find centripetal acceleration. Centripetal acceleration is a function of angular speed. Centripetal acceleration is a function of linear speed. Notice that centripetal acceleration is proportional to the square of the speed.